Okay, so let's look at a couple of different functions here. They're gonna be pretty unique. Use your graphing calculator. Make sure you're in radian mode. And let's just look at these guys. And what I would recommend is when you're trying to figure out the domain and range of one of these guys, what I would do is on your window screen, I would set your x interval to be equal to pi over 4. And I would set your x min and x max to go from negative 2 pi to 2 pi. The reason I would do this is because it gives you a good look at what your graph is going to look like. It makes it bearable. You know what each tick mark represents. And then your y values can change based upon what you need. So you can set your y values to be as large or small as you need. Well, here is the graph of the tangent of x, absolute value tangent of x. Looks like this. And the interesting thing about this, remember, is with tangent, the normal tangent should have these guys under the x-axis, okay? We should have these pieces under the x-axis, but we don't. And since we don't have those pieces under the x-axis, what we've got is some different range issues. So the domain, what domain can we use? Well, with the tangent, we've got those asymptotes, and those asymptotes continue to occur just like they always have. And on this graph, I marked off pi over 4 units as my tick marks on the x. And so you can see on here that every other pi over 4 unit, I have an asymptote. Well, what does that mean? That means that this unit right here is going to be pi over 2. Okay? At pi over 2, I've got an asymptote. And so what is my domain? My domain is going to be all numbers. It's going to go from negative infinity to infinity, except for at those places where we're not equal to some form of pi over 2 plus k pi. And what this gives us is every pi units, it gives us an asymptote. So here's our range right here. Here's our range. You know, you could say the set of all x is such that, or however you most are comfortable. But the important key, the big part of this is this part right here. Remember, the period of the tangent is pi. And so that means every pi units we're going to have an asymptote. Now, the domain on this guy is going to be interesting because we don't have any values less than 0. And so the domain on this guy is going to go from 0 to infinity. And so it's going to be really a strange thing to look at, you know, as far as how we're used to seeing. It's going to look like a bunch of little parabolas there, but that's what it is. We don't have any, we take no space up below the x-axis. Everything below the x-axis is completely open, and so there's nothing there. I mean, look, there's nothing down here that's being used. And so since the domain is not being used down here at all, then we have to say that, you know what, it's just not, it's not defined down there. So since it's not defined down there, it's got to be, you know, it's obviously defined somewhere. And in this case, it's actually going to be everything above the x-axis. Okay? And then the period on this, how often does this thing occur? How often does it repeat itself? How often do we get the same shape? Well, how often is it? It's every pi units. Every pi units we get one of these shapes. And so the period in this case is still going to just be pi for the entire shape to repeat itself. Now, what about the next graph here, the sine of x? Well, on this one, you want to change your y window a little bit. On the tangent graph, I went from negative 10 to 10 for my y values. I am not going to do that for my sine curve. I'm going to use from negative 3 to 3 on my y values, but I'm still going to keep all the other stuff. So I still have an x min and an x max of negative 2 pi to pi. Okay, and I still am breaking my graph up into units of each of these units right here is pi over 4. So That way I can still keep track of some things. That's pi over 4. So if I go 4 of those units, I am at pi. Well, if I start at 0 and go out to pi, let's talk about period real quick. From 0 to pi. Look, one full use of the graph, one full completion of the graph, one full, hey, we used all the values we're going to use on this graph. So the period on this guy, the period on my tan function didn't change. The period on tangent's always pi. Well, check out this guy. The period on this guy, he's also pi. And that doesn't happen all the time. You have to look at the graph and what values of y are being used or not used. And then what about the range? Well, the range are all the y values that are being used. And hey, just like the previous problem, we don't have anything being used under the x-axis. So our range is going to go from 0 up to what? From 0 all the way up to 1. From 0 up to 1. That's our range on this guy. And you know what? I think I've got my tangent stuff labeled backwards. This should be range and this should be domain. So let's fix that while we're over here. Domain and range. And so, what's next then? Well, domain. The domain on this guy, what values of x can we put in? Hey, guess what? We can put in every single value of x. We're not restricted at all on what goes into this function. If you were to zoom your x-axis all the way out, this thing would just bunny hop out there forever and ever and ever. And so what values of x cannot be used? Where do you have an asymptote? Well, on absolute value of sine, you don't have an asymptote. So all those values are being used. Okay, what parallel lines does the trig function oscillate between? And we looked earlier at how things move around when you add or subtract something to your trig function. Well, I want you to look at the window that I'm going to use for my graph. Okay, it's going to be this right here. And by the way, this goofy, long, nasty looking number is just negative 2 pi. This is positive 2 pi. And this guy right here is just pi over 4. And I like to use those numbers when I graph and trig, just so I can I know where pi over 4 is on my unit circle. I know what I'm looking at. So I like to use that guy. Well, here's our graph right here. Notice that it definitely is oscillating. It's got this wave feature, just like if we were to graph it normally. But hey, guess what? It does oscillate between two things. And if we change our x mins and maxes and our y mins and maxes, we'll see that it does bounce back and forth between a couple of values. So look, like here's a, let's see if I can get it lined up right. So here's a parallel line. It's not cooperating with me. There we go. Oh, it's got a mind of its own. And this guy, if we look at him, I'll line him up and then I'll clone him. And when he gets cloned, he doesn't change his shape or his slope. His slope will be the same. So I'll just clone him real quick. And there's another one. And look, it popped out perfect. It popped out right where it needed to. Notice that these two parallel lines now border my graph. And if you want to know what's going to happen to your graph, all you've got to do is look at what you're going to add or subtract. So what two parallel lines border this graph? Well, keep in mind that the sign always goes between, it goes up 1 and it goes down 1. So I'm actually on this graph bordering between parallel lines of y equals 0.5x. Okay, 0.5x plus what? Well, in this case right here it would be minus 1, and y equals 0.5x plus 1. And that's where those guys are rolling through. And it's just really interesting how all that stuff happens. It's just kind of fun to mess with, to look at and explore how these things change. So that's it, though. That's the two parallel lines that happen. And you can do this with any sine or cosine function. They will bounce back and forth in between those two lines. So there you go. Okay, so we want to determine whether any of these are a sinusoid or not a sinusoid. In other words, do any of these guys look like a sine or cosine curve, or do they have some totally different shape? Well, here's the window that I'm going to use for my calculator. I'm going to go from, again, just like in the previous problems, this is going to be negative 2 pi and positive 2 pi, and then pi over 4 for this guy. And then my y values, I just went from negative 7 to 7. I'm looking at what I could max out at here for my amplitude. So so I'm from negative 7 to 7. And it gave me the graph that we're getting ready to look at. So that's my setup for this. And then I just graphed this guy on my calculator. So here's the first one. Let me get it over here. Here's the very first one. It looks like this. This is number A. We'll put it right here. We'll call it A. And the question is, does this look like a sinusoid or not? And I don't know. What do you think? I mean, it looks an awfully lot like a sine curve that we've seen before. I don't know why it wouldn't have, be considered a sinusoid when you think about, what is sinusoid? What is it supposed to do? It's supposed to have this wave shape, a consistent wave shape. There's not any big differences that we can tell with our eye. And because of that, I would say that this one represents a sinusoid. OID. So I would say this one represents a sinusoid. Based on how it looks, there's some things that we're going to learn later that will allow us to prove that yes, it truly is one. But this is that guy. So there you go. So part A, he works. He's a sinusoid. Well, let's look at part B. Part B looks like this. So here's part B, and let's get rid of that one and put up a different one here. Here's part B. There we go, that's better. There's part B right there. And right off the bat with part B, you should notice that, hey, things are not the same. Things aren't, it's not a pretty curve. It's not consistent between its maximums and its minimums. They change all the time. Notice that it's got like some funky wave deal going on here, where it like it's down, it's up, it's way down, it's up, it's in, and then way down, and then it's down a little bit, up a little bit, down a little bit, big up again. So nowhere near as consistent. Remember, a sinusoid has got to have that nice gentle curve shape, and this guy doesn't have it. So this one right here, we'll call him part B. B is no go. B is no sinusoid. Okay. And he's just it's not happening. So just a big fat no. Let's look at part C. Let's look at the third guy here, and maybe based off these three, we can make a conjecture about the last one. So here's C. Let's look at C, and again, I don't see that it has a real pretty curve. It dips down, way down here. It takes its time going up. It's got this real gentle curve in the middle. It's not consistent. It's not normal. It's not right as far as looking for a consistent period like part A. So this guy, for the same reasons that B doesn't work, this guy also is a big fat no. He's not a sinusoid. He's not a normal sine curve graph. Now, come back up here and let's look at what's going on here. Inside the sine and cosine, even though they're different, the periods are the exact same. But look what's going on part 2. 5x and 3x. Those are different periods. And remember that sine and cosine have a period of 2 pi. Well, again, look at the last guy. Here's a cosine, here's another cosine. But guess what? They're not the same period. And so in order to get the sinusoid, you've got to have the period has to be the same. Now, you could have a sine and a cosine graph and put them together, no problem. But the periods have to be the same if you want a sinusoidal shape. And so look down here on this last guy. It's got all these weird things going. It's got A cosine 3x, B cosine 3x, C. So A, B, and C, I mean, I don't know what to do with these. I can't graph these on my calculator and look at them. Oh no, right? Well, no, don't panic, because what you can do is you just come in here and look at the middles. What's going on in the middle? What's the period on all these guys? And I don't know what the period is on all these guys right off the top of my head, but I do know, because they all have the exact same thing in there, all the periods are the same. And if all the periods are the same, and you're dealing with a sine or cosine curve, then you're going to have a sinusoidal shape. So is this guy a sinusoid? And the answer is yes, he is.